Yes. Then there's a clicker here with a laser pointer.
Fantastic. Thank you very much.
Your time is unfortunately blocked if you're short like me and standing here, but maybe you can see it over there.
Oh, great. That's fantastic.
There. But,
Yeah. In my field. Great.
Perfect. And I'll just stand up at like your overtime.
Yeah.
To give you a signal.
Yeah.
But we program in a lot of
yeah.
stuff. So.
Thanks very much.
Wait a couple of minutes. So your timer? Awesome. I visited for the dust conference.
Yeah. That was right before I moved there.
Oh.
I was supposed to be there at that point, but I was waiting for my Swedish.
Okay, good morning, everyone.
Good morning.
We're going to start day 3. We are now in our Understanding Galaxy Evolution through Chemical Enrichment section. So yesterday we learned a little bit about stellar deaths and how supernovae, AGB stars, Wolf rays can enrich the environment. Now we're going to be talking about chemical enrichment a bit more generally on galactic scales in the next 4 talks. So we have Clark, who will be talking about modeling cosmic dust evolution atom by atom in a multi-phase.
Okay. Hi, everyone. Thanks very much for coming, and thank you to the organizers for what's been a fantastic conference thus far. I'm Clark Marian. I'm a postdoctoral researcher at Chalmers University in Gothenburg, Sweden. As part of this Origin and Fate of Dust in Our Universe collaboration. And I'll be talking today about some of the theoretical work that we're doing to try and better understand dust physics processes in the ISM. So I don't need to motivate dust to this audience, but just for context, I'll talk about some of the open questions that we're trying to address. So as you all know, the properties of dust are non-uniform and evolving in the interstellar medium. And there are many processes which determine its amount and material properties, but they're complicated and consequently remain incompletely understood. So as we saw from some great talks yesterday, we think that the dust nucleates in the remnants of evolved stars, supernovae, AGB stars, Wolf Rayet stars. We think that that there is a transfer of mass between the gas phase and the grains, both via accretion as a way of growing the dust and sublimation and thermal sputtering as a way of eroding the dust. As well, we think that the grains collide with each other, which can have a number of outcomes. And of course, all of these, with the exception of nucleation, we think are occurring simultaneously in interstellar shocks, which are probably important for dust processing. So a complete physical understanding of the cosmic dust life cycle will require accounting for all of these processes and their interaction in a turbulent multi-phase ISM. Right, and so I'm going to talk about a subset of these processes today. Those are the ones highlighted. Right, and so the way that we're trying to place constraints on these processes is through molecular dynamics simulations. So I think these might actually be the smallest simulations, smallest scale simulations ever run of the ISM. I'm not entirely sure, but it seems reasonable. Right, so unlike many of the atomic and ionic processes in the ISM, dust physics processes are have involved many more particles, which make them very difficult to tackle pen and paper analytically, and so they usually have to be characterized numerically or empirically. Now with sort of modern computing and numerical technologies, we can get closer to first principles estimates for some of these processes with molecular dynamics simulations, of which hopefully this will play. So those are two small dust grains, which for which we're simulating their dynamics and the formation and breaking of chemical bonds. Well, it's not letting me play it again. Anyways, right. So, so the methods that we use, to be clear, solving the full many-body Schrodinger equation, even for the smallest dust grains, is still too computationally intensive. So we use two levels of approximation. The first is density functional theory, which is fully quantum mechanical, but it's based only on, primarily on the electron density field, as opposed to the many-body wave function. And this density field is mapped onto the total energy, which then determines the dynamics. So this is a fairly accurate method, but it's expensive. And so we only use it for calculating structures that are close to equilibrium. So like finding the material structures and calculating binding energies. The other method is this reactive force field, ReactFF method, which evolves the dynamics of the atoms classically with parameterized and empirically calibrated potentials that account for the formation and destruction of bonds and therefore chemical reactions. This is less accurate, but it's cheaper, and so it's the one that we have to use for modeling the more complicated and rapidly evolving dynamical processes. Right, so just a bit of background on this first process that I'm going to talk about, the gas phase accretion. So you can parameterize, you can sort of write down the growth rate of an individual interstellar dust grain as a sum over all of the gas phase, due to this accretion process, as the sum over all gas phase species, labeled by I, their product of the individual particle mass, their number density, and the velocity average cross-section. And then, assuming Maxwell-Boltzmann and that the grains are compact spheres, you get something like this, for which there is this factor which we call the sticking coefficient. So it's the thermally average probability of any one of these particles which hits the dust grain actually sticking to it. And this isn't unity because the particle can sort of bounce off the dust grain. And its dynamics are, of course, dependent on the complicated molecular geometry on the surface of the grain. And so these are very uncertain, but I just want to argue why this accretion process might be important. So if you do sort of order of magnitude estimates of this growth rate, and then you use that to estimate a grain growth timescale, when you factor out the sticking coefficient dependence and assume reasonable values for the local ISM, then you get that this growth timescale for the dense molecular phase, the diffuse molecular phase, and the cold neutral medium are all about 1 megayear, which is pretty short on astrophysical timescales. Even in the much more diffuse warm neutral medium, it's about 10 megayears. And so this is telling us that if sticking coefficients are of order 0.1 or larger, then grain growth can reasonably happen on timescales comparable to or shorter than the lifetimes of molecular clouds, and are probably important for setting the grain composition. Right, so we're estimating these with molecular dynamics simulations. These were mainly run by my collaborator Duncan Bossillon at the University of Rennes. And what he did is he constructed this amorphous carbon cube, which is approximately 20 angstroms on each side. And then we throw atoms of all of the different elements that are in the interstellar medium at it and see if they stick. We already did this for environments that are more relevant to nucleation processes, and so now we're expanding it to the gas and grain temperatures that are relevant for ISM conditions. This is a wide parameter space, so we ultimately hope to train a neural network to predict this, but that's work in progress. But I can still show you the results of the molecular dynamics simulations. So here are the sticking coefficients as a function of gas temperature for the most abundant elements in the interstellar medium that we're able to simulate. The color of the data points is showing the gas temperature that it's assumed for the calculation. And the main thing to note, I would say, is that for almost all of these elements at most gas temperatures, sticking coefficients are much larger than comparable to or larger than 10%. So this sticking coefficient is not necessarily an inhibition to the growth of carbonaceous dust in the interstellar medium. The one very interesting counterexample, which we need to add more points to, but it appears to be that the sticking coefficient goes to 0 for carbon below temperatures around 10 to the 40 Kelvin. We don't fully understand that, but it probably has something to do with the activation energy needed to break an existing bond on the surface of the grain in order for a new for a new atom to chemisorb onto the grain. Right, and so I'd say the key takeaways of this are that quite possibly pure carbon dust struggles to grow at temperatures characteristic of the cold ISM. Again, we need to fill this out. We're currently running molecular dynamics simulations to fill out the parameter space there, but that's what we see. And more robustly, non-hydrogen and carbon elements happily stick to amorphous pure carbon dust, which suggests that carbonaceous dust is easily polluted. And so I think that this is potentially important or worrying result of which the consequence is that we might need to reconsider this sort of two-population carbonaceous silicate paradigm for the interstellar dust population. Right, so we typically assume that the dust is composed of some carbonaceous grains and some silicate grains or some mixture of the two. And this is well motivated in the nucleation environments where the dust forms because carbon monoxide formation is the fastest process. And so it's whatever is left over from that, which determines the remaining gas phase abundances that can form the dust. And even the most sophisticated current models for the interstellar dust, which do allow for composite grains, assume that the carbonaceous and silicate components are spatially segregated. Whereas the results that I'm showing would suggest that they can be pretty well mixed. And so this might indicate a need to consider a much larger set of material compositions and therefore optical properties when we're trying to understand interstellar dust. Of course, there's a lot more that we're working on immediately. We want to get this for the rest of the remaining elements, either through more molecular dynamic calculations or neural network. We want to do this for hydrocarbons, which we think are a more realistic representation of the carbon-carrying dust in the ISM. Also want to do it for silicates, and then also look at the effect of ice mantles, sublimation, and desorption. Right, and so now I'm going to talk about the other sort of main process for which we have results, and it's grain-grain collisions. So the grains can collide with each other. We know that they have this wide size distribution. Grain-grain collisions might reasonably have a part to play in setting that. And so when the grains collide with each other, depending on their relative velocities, they can coagulate, they can shatter, or they can completely vaporize, which is the velocities are so high that everything is immediately returned to the gas phase. And so the traditional thresholds for this are order 1 kilometer per second for shattering, and then 20-ish kilometers per second for vaporization. And that's what we want to test with these molecular dynamic simulations. Again, just with order of magnitude estimates, you find that the frequency of these dust grains colliding with each other is fairly short on astrophysical timescales in ISM conditions. So this is probably an important process as well. Right, and so we're doing the same thing. We have these amorphous carbon clusters that we're sort of throwing at each other with different relative velocities to see how they behave. The one thing I'll note is that computational limitations prevent us from simulating clusters that are much larger than 50 angstroms in radius. So these are the very smallest grains on the small side of the grain size distribution, but that's all we can do at this point, and hopefully we can learn something from these nonetheless. Right, so what we can look at is we can throw these clusters at each other with a range of impact velocities and then see what survives. So here is the number of atoms in the largest surviving grain as a function of impact velocity for these amorphous carbon structures that are 7 angstroms approximately. And you see that the fragmentation seems to be happening at quite a bit higher than the canonical 1.2 kilometers per second value, which is typically used. We can do this, we can assess the impact of the impact angle, which doesn't seem to be particularly important because they're amorphous. And then we can do this for as large a grain as we can simulate. And in general, we see that these grains tend to be pretty robust up to almost a factor of perhaps 3 higher than the traditional threshold. I'm going to skip that because I'm running out of time. We've also done this for clusters that we've created ourselves using the determined composition of silicates in the astrodust model. Again, another fun video. And you can do the same thing. And again, we're kind of seeing these higher collision velocity thresholds for fragmentation. But I will also note that the threshold for vaporization, where you basically don't have a dust grain anymore, appears to be much lower. It's order 10 kilometers per second, almost a factor of 2 lower than the canonical value. I wish I could play all of these, but I'll just go to my summary. So yeah, these thresholds that we're calculating from the molecular dynamics simulations, they seem like they might be factors of several off from the traditional assumed thresholds from classical calculations. Of course, there's much more to do. There are uncertainties in the molecular dynamics methods, so we're going to check some of them with DFT. We want to understand the discrepancies between these previous results. Also, we want to do larger grains, analyze shattered grain size distributions, of course, all different grain compositions. And finally, what I'm most interested in is ultimately putting this all together for a model of grain evolution in the interstellar medium. So I got my PhD doing galaxy formation simulations, fluid dynamical simulations. And so what I'm developing now are sort of kiloparsec scale box simulations of the interstellar medium that incorporate the results of all of this complicated dust physics so that we can predict the observable properties of dust in a way that's fully coupled to the physics that's processing it. And so stay tuned for that. Thanks very much.
Thank you so much, Clark. That talk has me giddy.
Oh, great.
It was so wonderful.
If you are someone who is normally using grid models or Themis, what kind of effect would you anticipate there being of when you're comparing, your modeling work with theirs and you're seeing these discrepancies, what?
Yeah, so I mean, this is all fairly new, so we don't have detailed quantitative predictions in that regards. Like I said, if it's really the case that these these carbonaceous dust are it's polluted with all of these other elements, then we would want to predict what the optical properties of those materials are, which I don't think has been done yet, at least to my knowledge. Maybe I'm wrong about that. Sorry.
So many questions. Greg.
So given that it looks like you won't get the growth of large, just pure carbon grains, have you tried beginning with a small grain and then just throwing things in a portion and just seeing how it grows over time?
Yeah. So that's a good point. So what we do with the grain growth simulations is that it's basically, we hit one atom each time, and so we're not changing the composition of the grain as we continue to calculate these sticking coefficients, because of course that might change the sticking coefficient. So no, we haven't done that yet, but that's obviously very interesting.
Also, if I have a follow-up, could you just show, you said there was a video you couldn't show.
Oh, that was just because I was skipping ahead, but it's just more of this.
Let's go on this side. Over there.
I just wanted to clarify what it means by sticking coefficient.
Yeah.
So if you look at your sticking coefficient, you calculate well above 1,000 kelvins, but usually people assume the sublimation temperature of dust is 1,000 Kelvin. So how can you stick the dust?
Well, so to be clear, these temperatures are the temperatures of the gas particle. We're only going up to these temperatures on the x-axis are the gas temperature of the impacting particle. The color is the dust temperature, of which the maximum we assume is 300 Kelvin, which I think is more reasonable.
Remy?
I know you said you haven't done hydrocarbons yet, but would you care to speculate on how easy it is to make PAHs in the cold neutral medium from molecular progenitors?
I'm not willing to do that.
We have time for one more. Yeah.
Oh, so you showed that the range between shatter and vaporize is narrower than perhaps expected, but I was wondering if you were able to, or maybe in the future, are able to simulate larger grains. Do you think that range might be wider for them?
Well, we're trying. We're really trying. I mean, at the very least, I'm bugging my molecular dynamicist collaborators, being like, so how big can we really go? They're like, oh, it takes so much time. I'm like, okay, but in principle, if we were to run it for like a month on the supercomputer. So yeah, of course, the bigger the grain, the more, the more representative it is of a larger fraction of the dust grains that we think exist in the interstellar medium. But yeah, this is a computational limitation.
Awesome. Let's thank Clark again.
Thanks.
Oh, now you're spoiling the end.
I know, I'm so sorry.
Oh, no.
There we go.
Yes, thank you very much.
Is up there?
I hope so.
Okay, great. So this is the clicker. And it's going to be right there.
Okay. Yes. Yeah. Okay. Cool.
Take it away. Now we have Stefan talking about disentangling galaxy and dust evolution mechanisms through chemical abundances.
Yes, thank you very much. I first of all want to thank the SOC and everyone that selected me to give a talk about the work that I've been doing during my PhD, and also giving me the opportunity to bridge all the detailed work that has been going on in the Milky Way, and also more detailed on dust physics, to slowly move towards the nearby universe and nearby galaxies, to actually apply this to potentially figure out whether dust is primarily formed in stars, or maybe there is a different mechanism. I'm doing this from the point of view of chemical evolution, where we simply are looking at the quantities rather than the dynamics, where we look at how much gas enters a system, in this case a galaxy, how it gets reprocessed within the galaxy through star formation and then the fusion of elements to the heavier elements, and then also through outflows fueled by different feedback mechanisms. This is purely based on the interaction between the gas and also how gas transforms into heavier elements, but we also are interested in dust, since a lot of the elements can be locked up into dust grains. As has been shown in different literature for the Milky Way, for example, where depending on the relevant ratio of certain heavy elements that can be likely locked up into dust grains or not be locked up into dust grains, we actually see that depending on the elements, it gets either heavily depleted or not depleted at all relative to the relative metal abundance. So then we have to ask the question whether the formation is, or whether the elements are primarily locked up in the dust grains, or whether it is just purely stars that is forming the dust and automatically locks it up there. This is primarily also fueled by studies from global galaxy properties, where we are looking at the dust-to-gas ratio varying, the dust-gas ratio varying with the metallicity, where above a certain metallicity threshold, then the dust-to-gas ratio linearly scales with the metallicity, but below there is a different trend depending on the types of sources that you're looking at, where it's either remaining linear or there's a steep decrease, which begs the question then, are stars indeed is the difference between the formation mechanisms the reason for the different slopes in a dust-to-gas ratio, or whether there's just simply a selection bias for the targets. So with chemical evolution models, we can actually link the formation of different elements to the formation of dust, since dust and gas phase elements are made of the same composition. The problem then becomes for the global galaxy studies that there are a lot of different chemical evolution models that are trying to constrain this effect. And also all these models are trying to constrain the dust accretion timescale if dust accretion is needed to see whether we could then solve the missing dust budget. And the results are different. There are plenty of recent studies that showcase that accretion is a dominant factor, where you get dust accretion timescales of up to 10 megayears. But there are also plenty of studies that motivate that stardust is the most dominant factor when it comes to dust growth, as has been showcased by Ilse de Loze. So we have two problems. One, actually, that we are looking at global galaxy properties, and if we are looking already now in nearby galaxies, such as with the Fang survey, we notice that there is a radial distribution of the physical properties, such as the radial distribution of stars and dust is completely different. And also when it comes to the chemical evolution models, depending on the models that you're using, then they can create degenerate effects that will result in different conclusions when it comes to whether accretion is dominant or not. So that's where my my studies come in, where I'm actually looking at nearby galaxies on spatially resolved scales and trying to see if we were to simply look at a single galaxy, or in this case 4 different galaxies, and look how the radial properties differ, whether that is then a potential evidence of whether dust accretion is an important fact to explain the dust radial profile, and also get an idea whether dust accretion is needed. So the galaxies that I'm showing here, NGC 628, M11, M33, and NGC 300, are the galaxies that I'm investigating. I'm not the first one that is investigating these galaxies, so there's already a lot of literature at hand that I can use to analyze them. And an important part for these 4 galaxies is they slightly differ in morphology, so then that way we can trace a little bit the different types of galaxies that we can expect in the nearby universe. And also more importantly, the oxygen abundance radial gradient is completely different for these 4 galaxies. Usually we bin them in 2 different ways. We have NGC 628 and M11, which are extremely metal rich in the center and also have a steeper slope, especially M11. And then you have M33 and NGC 300, which are a little less metal rich or oxygen rich, and also have a shallower radial gradient. So that can already be used to disentangle whether dust growth can be either stellar dominated or accretion dominated in a specific way. We are also looking at the radial profiles to see whether we can already see evidence whether it's different. If we were to, for example, look at the dust to gas ratio, an important tracer, then we see that the radial variation is either similar or quite chaotic, especially for M101. If we're looking at the dust to stellar mass ratio to get an idea whether dust accretion is needed, then with increasing radius, then the dust to stellar mass ratio is increasing. So that can already be signed that at least the dust buildup is more efficient in the outskirts. So that can maybe be an indication for dust accretion. But this is all pure what we are seeing. Now we want to figure out whether this is also seen in a chemical evolution point of view. So in this way, that's why I've updated an existing dust chemical evolution model, Chemiful, which is a result from the Dustpedia collaboration, and I've updated this in a way we can now use assumptions that are made for Milky Way chemical evolution models, and in addition add a dust evolution model, both from stellar production and also from dust accretion, to try and see how efficient dust growth needs to be to get the resulting dust masses in the end. I'm doing this in 2 steps. The first step is that I'm first constraining the stellar evolution, primarily to see how the metals need to be milled up to get the observations that we have and also the base of the metals. Once that's constrained, then we can switch to how dust growth later on, so that we do not bias our stellar evolution based on the dust production in the end. So for now, I'm going to focus on the results that I have for the stellar buildup, where I vary 4 parameters: the star formation efficiency, the gas accretion timescale, so how much time it's needed for gas to accrete on the system, the initial gas mass infrared, just a simple scalar to scale how much gas enters the system, and also the mass loading factor, how much gas exits a system per supernova event. So these are then the results where I use the stellar mass surface density, gas mass surface density, the star formation rate surface density, and the oxygen abundances as my constraints. Here for NGC 608 and M101, the metal-rich galaxies, and we can already see that it is close to a perfect match as we can get. There aren't that many data points because the fits are still running, but we can already see it for the outskirts. It almost perfectly fits in the 4 constraints, and for M101, it is a very good fit. Then for M33, it is also a very good constraint fit for all the 4 constraints. For NGC 300, we can already notice that the fit has a lot of issues, especially for the star formation rate, surface density, and oxygen abundance. But if we look at the gradient, then that at least seems to overlap. It's mostly just the absolute values that differ, which has to mostly be related in as NGC 300 is the smallest galaxy in the sample, and therefore is also the bit trickier to actually constrain the stellar evolution. Now, it's time to investigate actually the best fit parameters to try and see whether we can already make some small conclusions on how the stars are built up. If you look at the parameters that seem to correlate quite well, we see that the star formation efficiency decreases with radius. That is a small evidence that star formation is less efficient in the outskirts, and that there also is an evidence that star formation happens earlier on in the center relative to the outskirts, a result well known as the inside-out growth theory. And we also noticed that for the gas, that it actually is slower entering the system in the center, and also that the outflow, the mass loading factor is higher in the outskirts, where a lot of the material actually gets pushed out in the outskirts. Now, if you then compare this for all 4 galaxies, we see that especially the star formation rate efficiency and the mass loading factor are consistent for 3 out of the 4 galaxies. And even though NGC 608 has a lot lower star formation efficiency, the slope seems to be the same. So in this way, it seems that we can already confirm that inside-out growth exists. So in that way, our methodology works from the stellar buildup. Now we can focus on the dust buildup. But first, since we are fitting, we can actually look and see how good are their fit results. And here are a bit more tricks under the carpet, where there are actually 2 best fit results in our analysis. For NGC 608 and M101, we actually noticed that there are 2 peaks. One peak where you have where you are extremely efficient in the star formation, but then your initial gas mass is relatively low, so then you have a slower mass buildup of stars. And you also have the results where your star formation efficiency is a lot lower, but your initial gas mass is a lot higher. So then a lot more stars are built in the beginning. When analyzing results, I concluded that the peak where you have a slower stellar mass buildup fits better. And this is also consistent with M33 and NGC 300, where you only have 1 best fit results, being the slow stellar mass buildup. Now, the big question, do we actually need dust accretion, or is the stellar buildup that we have constrained the only thing that we need? And the answer is yes. If we simply take different dust production efficiencies for grain growth and also dust destruction in case we overproduce the amount of dust, we notice that for the blue line, which is where we only consider stellar dust buildup, that it can already explain the dust mass radial profile for M101. If you want to get higher values, then you need extremely efficient dust accretion, the green line here. So in this sense, we do not need dust accretion. It's only an addition, but in general, the stellar mass buildup is good enough. It comes with the caveat that, in this case, I'm not implementing the destruction of dust grains from the first shock. simply just a production from supernovae and HB stars. If I were to implement that, then the blue line actually gets shifted down here. And in that sense, we do still need the green, but the green line never shifts. So the green line is always able to predict the dust mass radial profiles. So to conclude, I've already shown that just from the stellar mass buildup that the star formation history is indicated inside-out evolution in terms of the radial evolution, and also consistently that the star formation efficiency and specific also the mass loading factor shows consistent trends for all the three galaxies. I also noticed that for the dust mass, to recover the dust mass radial profile, you only need the stellar mass buildup. That also, and you can explain it with the short accretion timescales, but it's not needed. So in this way, we can actually use this chemical evolution framework to try and constrain whether dust growth is primarily done by stars or whether you also need the accretion to explain what we observe. Thank you.
Thanks so much, Stefan. Questions?
So where and how dusty gas accrete and how dusty is it in these models?
So in these models, we are not looking at the specific location. In the models itself, we divide the galaxies into different rings, and then we assume that the gas falls in somewhere in this ring, but we do not have specific locations. It's all radial averages in this way.
Sorry, but where, I mean, at what radius?
Oh, at what radius?
Edge, in the middle?
It's across the entire disk. So that already is a bit.
That's a pre-parameter, or you're?
No. So in every single ring, we assume it's its own system. So there is gas inflow in every single ring by itself, and then depending on that, the quantity can be different or not. But we do not assume that gas falls into a certain radius, and then from there it spreads out towards the other rings. It's 10 different chemical evolution models for every single ring by itself.
So, sorry, I'm sorry to be dumb, but are you then finding something that meets your data that constrains the rate of accretion in each ring?
Yes.
Okay,
yes.
So that'd be interesting to see.
Yeah.
Other questions? In the back over there.
Thank you for the talk. So, what's the total mass loading factor of these systems? How does compare with other galaxies that lower high redshifts? So the total rather than the
Total, I'm not sure about the total. If I were to look at the mass loading factor, the Milky Way value is around 0.1 right here. So the mass loading factor for all these galaxies is a lot higher. I have tested it to see whether if I were to fix the mass loading factor to the Milky Way value, whether I recover the oxygen abundance radial gradient, which is the trickiest physical property to constrain. And I found out that I cannot recover it with the fixed mass loading factor. So I needed to have it as a variable to get the results.
Other questions? I'll take chair prerogative to ask a question. Could you flip back to the dust to gas ratio versus metallicity plot that you had?
Oh, in the very beginning.
Yeah, in your intro. So I'm wondering if you have any plans. Selfishly, I study the galaxies over here.
Yes.
So I'm wondering if you have any plans where you can really probe that stardust regime, and if you can make your models try and predict things that are like a little bit less than SMC metallicities, about 20% or lower.
Yes. So there are plans, not by looking at low metallicity galaxies, but I have observations of M3D1, where we try to probe the metallicity distribution both in the H2 regions, which are now the primary tracers, to constrain the oxygen abundance, and also in the diffuse ionized gas. Then it's the idea to see how dust grows in the environments around H2 regions, or whether we can already find low metallicity regions in M31, where potentially dust grows in a different way, and that can be calibrated for dust growth models to see how dust growth is different for the dense phase ISM as well. But then the main focus for that now is to then look at the high and the low metallicity regimes.
Awesome.
question?
And Josh has one.
Josh again?
Yes, go ahead, go ahead.
How dusty is the gas that you accrete in the models?
There is no dust in the gas at the moment. The model itself does allow you to determine how much dust gets also accreted in the model itself. But for now, we assume that there's no dust in the gas that's accreted, and also that that the metallicity of the gas is pristine. There is, of course, a potential mechanism where you have a recycling of gas gets flown out and gets trapped in the circumgalactic medium. But that's something that I've not tested yet, because that will create degeneracies in how efficient then the recycling is of the material compared to how much accretion, gas accretion happens. But it is something that we can constrain with Milky Way values to have that fixed, rather than using now a toy model where everything is pristine in this way.
I guess I'll be the bearer of bad news that the CGM is pristine.
Yes, so then that would already be something that we can, that's already something that you can then implement in the models as well. It's one of the 3 initial conditions.
Any other questions? Okay, let's bake Stefan again.
You have 13 minutes. Okay, great. This helps you go through slides. Laser pointer right there. Awesome. Thanks. Take it away.
Testing. All right. Good morning, everyone. How are we all doing on this Wednesday morning, middle of the block? Anyone else from the West Coast still a little jet lagged? My name is Megan Barry. I'm here from UC Davis. So happy to be here in Baltimore today with all of you. And I have some, I think, cool results on how galaxies can form alpha element bimodalities. So especially mid-morning block Wednesday, what even is an alpha element bimodality? I'm going to go through a bunch of background, so I hope you guys can stay with me. It's a little jargon heavy, but I think it's some cool stuff. Fun galactic chemical evolution. So yeah, please stay with me through the background to the cool results at the end. So right away, what's an alpha element bimodality? To talk about that, first I have to specify what I mean by alpha element. So that is alpha as in alpha particle as in helium nucleus. So alpha element is a term used in galactic chemical evolution to refer to the elements produced from helium fusion. So these even numbered elements, oxygen, neon, magnesium, etc., built up from helium nuclei, alpha elements. But why I am interested in alpha elements is that they are the characteristic products of type 2 supernovae. So yeah, when I say alpha element, the reason I am even looking at these at all is because they trace kind of type 2 supernovae. These also produce iron. I'm going to treat that totally separately. We'll see why in a minute. But yeah, alpha elements, type 2 supernova products. Right, so possibly as a review, maybe as an introduction, to even begin to talk about galactic chemical evolution and alpha bimodalities and that stuff, I want to clearly state 3 key principles of galactic chemical evolution that I'm going to refer to. The first is that type 2 supernovae produce predominantly alpha elements and a little iron on short time scales. So of course, after star formation begins, these events turn on quickly, or they start to happen soon after star formation begins, and they also stop soon after star formation begins as the high mass stars run out. Second is that type 1a supernovae produce iron on longer time scales. So these events require white dwarfs; those take time to form. So not only is there a delay in when they turn on, but they also continue to occur basically indefinitely after star formation begins, because white dwarfs can continue to form for long periods of time. So we can kind of think of these two supernovae types as two different scales of timekeeping device. So type 2 supernovae are like a clock or a stopwatch on a short time scale, and 1A supernovae are like a calendar or something like that on a longer time scale. So we can use the different products of these events to try to trace things like star formation history, maybe merger history. That's the concept. And then third is that stellar atmospheres preserve the element abundances of the gas that they formed from. So this is kind of my big tie-in to the topic of the conference, Inter+Stellar, is that these stars put out some elements, new stars form from those from gas containing those elements, and those element abundances are basically locked into the star's atmosphere for the rest of its life. So we can sort of use element abundances in stellar atmospheres to study the history of the ISM through the galaxy's lifetime. So these three principles are very important to what I'm about to talk about. So quick recap: type 2 supernovae, alpha elements, short time scales; 1A supernovae, iron, long time scales. And we can study these different element abundances by looking at stars, the atmospheres of stars. All right, thanks for sticking with me through that. One more thing before I get to my results. Like I said, bit of a jargon-heavy topic. So this space is a plot commonly used in galactic chemical evolution. Any star you can put somewhere on this plot. So our axes here are iron over H and alpha over iron. So every star, I guess except POP3, will have some ratio of these elements. So for example, the sun, we know the sun is rich in iron, so they would go somewhere over here, on the right. We also know that the sun is pretty low in alpha over iron, so the sun would go somewhere in the bottom right here. So you could imagine populating this plot with the different stars of the whole galaxy. So why these axes? So iron over H, we can sort of think of as a time axis. Again, sort of, I know you're probably already thinking of why we cannot exactly do this, but in general, the oldest stars are going to be the most iron poor, and then as time goes on, we expect more and more iron to be produced. And I'm sure you're already thinking of, deposition events, mass metallicity relation, all this stuff, why this might not exactly be true, but, it's a starting point. Then the y-axis, alpha over iron. This is, again, sort of, because these axes are intertangled, it's kind of a big mess, but sort of, we can think of this as a history of the ratios of these two supernova types. So if there were more type 2 supernovae in the star's history, it will be more rich in alpha. And if there were, relatively more type 1A in this, in the galaxy's history when this star formed, it'll be more rich in iron relative to alpha. So now I'm going to sort of make a theoretical prediction based on our three principles of how we might expect this plot to look based on galactic chemical evolution. So just to make sure you're paying attention, I'm going to quiz you guys on the first part. So no need to shout it out, just quiz yourself. But the earliest stars in the galaxy, not including POP3 for the smart Alex out there, but the earliest stars in the galaxy, they would be low iron. Would you expect them to be up here or down here? Just answer to yourself, yes. If you said they would be high in alpha, you're right, because this would be before 1As have turned on. They would just be rich in alpha elements from type 2 supernovae. So the earliest stars will kind of just proceed in iron at kind of whatever the alpha over iron ratio of a core collapse supernova is. And then as time goes on, as 1As start to turn on, both within a single stellar population and just galaxy-wide, we expect this ratio to go down as these 1As produce more iron. All right, so this is the main concept behind the work I've been doing, is this plot and predictions in this plot. So thank you so much if you've made it this far. Let's take a second to absorb this all before I show you what this plot looks like for the Milky Way. All right, good job, everybody. Thank you so much for sticking with me. All right, so looking at this plot for the actual Milky Way, same axes, blah, blah, blah. Let's take a look. Whoa, what is that? So if we look at this plot in the Milky Way, we can see that there are these two separate bimodal, if you will, populations. This is not new, by the way. This has been known for at least a decade or two now. These populations have come to be known as the high alpha and low alpha populations. You may already know high alpha is kind of associated with the Milky Way thick disk. Low alpha is associated with the Milky Way thin disk. In the name of time, I'm not going to go into the disk stuff, but please ask me if you're interested after. Yeah, so this is kind of a mystery. It's not, I mean, we wouldn't necessarily expect the simple model to be correct, but it's also not obvious why it would look like this as opposed to, you know, something else. And what's more is, well, I of course couldn't come all the way to STSCI and not include some cool JWST results in my talk. So these, not my results, but we are starting to get this measurement for Andromeda, and you can see, or sorry, I also want to point out that this is a difficult measurement to get. You know, obviously you need individual stellar spectra, so you can't just get it for any galaxy. Milky Way is basically the only galaxy we have a lot of stars to make this measurement with, but just starting to get Andromeda, and interestingly enough, you can see it actually does kind of follow the theoretical prediction. It's a little early, there's not that many stars here, maybe there's some secret low alpha population, but maybe some galaxies follow the prediction, maybe some of them have this bimodal, maybe there's like a whole zoo of features in this space that we don't even know about. It's a pretty cool topic, and that is what I have been investigating in the fire simulation. Sorry, I may not have been clear, this is a simulation talk, but what I, sorry. But what I've been investigating is the origin of this bimodal feature in this element abundant space in the Milky Way. Why are there these two populations? And maybe how common is this feature? Do we expect it to be ubiquitous? Do we expect it to be rare? Yeah, so luckily for me, Sarah Loebman gave a great talk yesterday about some other results from the fire simulations. She gave a fantastic introduction, so I will try to keep this part brief. But I've been looking in the fire simulations. These are high-resolution cosmological simulations of individual galaxies. I've been looking at the Milky Way mass galaxies within fire. They include dark matter, gas, and stars. There's about 16 sets of initial conditions. Some of these have been like rerun. I've basically looked at every version of these simulations I could get my hands on to kind of hunt for this bimodal feature. We model stellar evolution, hydrodynamics, gas, metal mixing. So a lot of the stuff I need for this topic, looking at element abundance evolution. If you have more questions on fire, please talk to me at the end because I'm running a little low on time. All right, so let's get to the results. So I looked at, like I said, all the simulations, all the variations of these simulations I could get my hands on to see what this plot looks like in all of those. And most of them looked sort of like the prediction, more or less. You can kind of maybe see the hint of a second population down here, but most of the galaxies look something like this. But I did find 4 galaxies that do have a very clear separation between high and low alpha populations. So my first main result is just that it's not ubiquitous, but it's also not super rare that 4 of the 16 galaxies, or like sets of initial conditions, whatever you want to say, that I looked at do have this feature. So it happens sometimes. As to why it happens, using the magic of simulations, we can look not only at that plot, but we can also look how stars evolve through this space in time. So I'm about to show you a little animation of the same plot, but in bins of stellar age. So oldest stars first, and then we're going to see how the stars evolve through this space. And this line is where that goes like straight through the high and low, like that goes straight through the gap. So let's start this going. So as expected, they start in the top left. They do kind of follow the theoretical prediction, but then they kind of spread out in alpha and just drop straight down. And that is not, so if I can smooth that path out, so this is like a path through time of stars in this space. And this is very interesting because it's not obvious that that is how this would happen, right? Like maybe you would have, if you look just like at the background of this plot, you might think, oh, it goes like, it evolves as expected, and then maybe there's some kind of like gas deposition event that like resets the iron or something, and then maybe it would evolve like along the second path, but we do not see that. In all 4 of the galaxies, they look something like this, where they, for the high alpha track, they evolve as expected, and then all of a sudden, the stars kind of spread out in iron and go straight down at fixed iron. Yeah, and so another way you can see this is that this is the same plot split by formation radius of the stars. So you can see at all radii, they kind of follow the same path together at the beginning, and then they split up by radius. So this has something to do with the onset of the disk and the radial gradient. Sorry, people were looking at that. Yeah, this one's pretty fun. So I have this plot for all the galaxies. They all look very similar, where they kind of switch modes from as expected to spread out in iron and go straight down. So I'll squeeze in one last little result that is kind of ties it together. So if we look at the star formation rate, which is kind of what the supernova ratios are meant to inform us on in the first place, I'll highlight this shaded region. This is by look back time. This is when the transition occurs. So like this is the time over which we start to drop in alpha. This is when it starts to switch from high to low alpha. If we look at the star formation rate, we can see that that occurs right after a peak, or right after a drop, basically, in the star formation rate. And we see this for all 4 galaxies. So you can imagine that if there's a drop in star formation rate, the ratio of 1A to type 2 will kind of, the amount of 1A supernovae will kind of overtake the type 2 supernovae, and this blue line is the ratio of the 2 types, and we can see that indeed the 1A supernovae are taking over, causing that increase in iron and allowing this to drop at, allowing the high alpha to transition to low alpha. There's some gas fraction stuff I'll skip, but anyway, the point is that these transitions all occur after a drop, and a permanent drop also in star formation rate. Okay, I think I am getting a little close to my time, so I will summarize. So in summary, I found that 4 out of the 16 fire galaxies, initial conditions, whatever you want to say, show these strong bimodalities. They all, when it comes to transitioning from high to low alpha, they follow the expected track at first, and then switch to this like spread out drop down feature. They don't like reset and go back down. They all drop in alpha after a permanent drop in the star formation rate. Kind of skip the gas fraction stuff. I have a bunch more stuff. I looked at the thin and thick disks, lots of fun stuff. Please come talk to me. And thank you so much.
Thank you so much, Megan. We have time for a few questions. Yes, right over there.
Thank you for a nice talk. I was wondering, so you mentioned the only other galaxy we can kind of get this relation for in observations is M31. Have you looked at simulations of non-Milky Way-like galaxies and see what you get there?
Yes. Somebody else in my group did a project on this measurement for not Milky Way satellites, but like Milky Way satellite mass simulated galaxies. They're not really bimodal, but that does exist. And this measurement does also exist like for the LMC, some other Milky Way satellites. Yeah.
And does it, I mean, would you expect it to be any different for galaxies further away from the Milky Way, like outside of the local group?
It does seem, we do expect there to be kind of special information about disk galaxies for this, just because I kind of glossed over in the name of time, but it is pretty established that the thick disk of the Milky Way is like these. Oh wait, I have a plot for this. If you look at, yeah, so this is plotting the spatial location of like the high alpha and the low alpha stars, and you can see like, I guess this isn't showing up super well on the projector, but you can see that's like, it is the thicker disk and then this radially extended thin disk. So I think a big motivation for the interest in this topic for the Milky Way and other disk galaxies is this association between high alpha thick disk and low alpha thin disk.
Thank you.
Sorry, in the back in the red shirt.
Thanks for the great talk. So now I'm kind of wondering, you explained well why the 4 of 16 seem to have this bimodality, but what's up with the other 12 of 16? Have they just not had time to obtain this lower alpha abundance, or is there something else going on as to why they don't?
So this is going beyond the current analysis I have done. I haven't started like analyzing in detail the non-bimodal galaxies, but I do have my personal speculation that I can give you is that if you, like I kind of mentioned on this one, you can kind of see the hint of what you could possibly call a low alpha population. And this does come up, like I've been calling like striations. Some of them have these little like stripes. So if you ask me, this is not part of this paper, so this is off the record, I guess. I don't know. There seems to be some kind of like spectrum of this feature where like all the non-bimodal galaxies, they do spread out. Like the radial gradient develops. Oh yeah, you can see. I have my other, the other animations I have by radius, so you can see that like when this spreads out, this is from the radial gradient, like along the disk. There's different element abundances, and the non-bimodal galaxies do have that. So I think it seems to be there's just different degrees of it, and these were just the strongest degree because maybe they had a very low gas fraction, or there was just some nice timing involved.
I have time for one quick question. Janice?
Going back to the bimodal galaxies, so why did the star formation rate suddenly drop? Do you know why?
Good question. Yes. So I don't have time to go through them all, but these 4 galaxies basically have totally different like merger histories, like different events that happen. Let's see. This is so this is the star formation rate and the gas that doesn't help that much. Some of them have So the one, they're all different. They're all different. Yeah, this one, the one we looked at had, for example, it had this like satellite make a near pass, and that's why the star this bump in the gas fraction was from like a satellite stream basically falling in, and then it stops, and then the star formation rate goes down, and that's the story for that one. Like some of them have like a big crazy merger, some of them have 0 mergers basically. Yeah, there's a fun variety.
Great. Let's thank Megan again. All right, next we have Christopher Garling, who's going to be talking about connecting metallicity evolution models to resolved star formation histories. Very, very Interstellar. Switch right here between slides. That's a laser pointer. You can have your time right there. You'll be sitting behind it this whole time. You should know. And just make sure the microphone is on. Did you set the switch?
She did.
Great.
All right, thank you for the introduction. I'd like to thank the organizing committee for putting on such a fantastic conference so far. And I'd also like to thank Sarah Loebman and Megan, who just spoke, for introducing hydrodynamic simulations so I don't have to do quite as much background. So my talk is really going to be about extragalactic chemical evolution. So we've heard some so far this week about going to lower metallicities than the Milky Way, and also about the time axis of chemical evolution. But this talk is really about extragalactic chemical evolution, and additionally on how we can connect that into the Milky Way studies. And so from extragalactic surveys, so specifically things like SDSS, we have observationally well-established relationships between the stellar mass of galaxies and their gas phase metallicities. So these are ISM metallicities that are based on metal emission lines. And this is a fairly tight correlation over many orders of magnitude. And in the local group, this extends also into the dwarf regime below 10 to the 9 solar masses. But what's interesting is that the slope of this power law extension of the mass metallicity relationship requires that these dwarf galaxies retain low fractions of their metals. And so, we've heard a lot about dust formation and the relationship that might have on metal content. And so what I'm really focusing here on is understanding the process by which galaxies enrich their ISM. So it should be pretty clear one place where this relationship could come from. The formation of new stars will give rise to new metals that are expelled into the ISM by supernova, and that enriches the ISM. But the metallicity of the ISM, quantified as the relative abundance of metals relative to hydrogen, is diluted also. And so the primary dilution comes from accretion of pristine gas from either the IGM or through a circumgalactic medium. But the effective chemical enrichment is also modulated by metal-loaded outflows. And so in these low-mass galaxies, I think it's on the next slide. Right, so in these low-mass galaxies, the dark matter halo potentials are also lower. And so the supernova can actually drive outflows that are not only loaded with hydrogen, but they're also loaded with metals to a higher degree than the ISM. And so this reduces the efficiency by which you're actually able to enrich the ISM through these star formation processes. So this shows an example of one of these metal-loaded outflows. This is a nice figure from the foggy simulations, which use specific numerical methods in order to better resolve the dynamics in the circumgalactic medium. And so they're very special in that way. And what you're seeing is in the white line, I've done my best to denote kind of the stellar disk of this object. And so as you expect, the sort of neutral ISM here extends further than the stellar disk, but there's also a very significant outflow, which here is shown in temperature. This is a hot outflow primarily, but then colored by metallicity, this outflow is metal loaded significantly more than the actual ISM. You can also see a pristine gas inflow that's being channeled into the ISM. And so this is really, at the intersection of these two processes. And so the effectiveness of these supernova-driven outflows is regulated by actually the subgrid supernova models. So because we are simulating whole galaxies and in some cases cosmological volumes, multiple megaparsecs on a side, we don't resolve the dynamics in the supernova expansion phases. And so virtually all simulations of this type will include subgrid models for how the supernova affects its surrounding ISM. So these are things like the proportion of energy that's put thermal energy versus momentum and things like this. And it also matters somewhat on the actual treatment of the hydrodynamics. So as Sarah Lobman showed in her talk, the fire simulations use a different non-SPH method for doing the hydrodynamics, which better resolves some of the turbulent structures that can be created during these supernova events. And so one way that's useful to think about the enrichment of the ISM in this context is to think about the metal retention fraction. And so this is pretty simply just the mass of metals that you retain over the mass of metals that you create originally. And so for high mass galaxies, this is of order unity. They're able to capture a lot of the metals that they create and retain them, and then that metal can go on to enrich the next generation of stars. But for low mass galaxies down here on this power law extension, this metal retention fraction is much less than 1. It can be as low as 10% or less, depending on the potential that you live in. Therefore, we expect the correlation between the star formation rate and the metal enrichment rate to also be different at these masses. So the cosmological volume simulations are typically able to reproduce redshift 0 mass metallicity relations fairly well. This one just shows the result from the illustrious TNG simulations, which I work on with Paul Torrey at University of Virginia. And you can see they fit these are slightly older results now, but generally most cosmological volume simulations can reproduce the present-day mass metallicity relation. However, they have significant differences when you start to factor in both the extension to lower stellar masses, but also the redshift dependence of the MZR. And so what I'm showing here is a nice figure by Alex Garcia, who's a grad student who works with Paul. And this shows these are 4 different cosmological simulations run with different feedback prescriptions. And they don't all produce the exact same redshift 0 result, but much more significant is the variation they predict both at low stellar masses and the redshift evolution. So the lines are colored by the redshift of the MZR. And then there's this inset that shows the offset from the present day value for each of these redshifts. And so what you see is, for example, in the Eagle simulation, this has a very precipitous change in the MZR as a function of redshift, whereas in the original illustrious model, that evolution is much, much lower. And so the present day MZR is only constraining in the very, very low mass regime, because most of these simulations can reproduce the high mass end of the present day MZR. But if you can press this back in time, if you can measure the MZR at earlier times, then this would allow you to differentiate between these feedback models. So historically, this has been pretty poorly constrained, below about 10 to the 9. There's been some recent James Webb work, which has really been extremely impressive, where they took, it was 51 dwarf galaxies that are behind a galaxy cluster, and so they're strongly lensed, and they were able to obtain stacked mass metallicity relations. And so if you look at the squares and the circles, are there measurements for individual galaxies? And you can see those relations are, it's hard to measure them for each individual galaxy, but when they stack the spectra and they do a joined stacked analysis, they're able to produce these 2 MZRs at, the blue is roughly Z of 2 and the red is roughly Z of 3. And so what they're showing here is that the slope is pretty different from what's been inferred before, but the slope is also not changing between redshift 2 and 3. And so this is the type of work that I'm interested in extending and that I think can help to constrain these supernova feedback models. And so I work mostly in the local universe, and so I was wondering if there was something that we could do that would be complementary to this work at higher redshift. And so we've seen a couple talks earlier in the week about determining stellar properties using programs like BEAST. And so those give you, posterior estimates for the properties of individual stars. But what I'm interested in are constraining the properties of a stellar population on the whole, right? And so this shows, this is just a color magnitude diagram simulation. So these are not real data. These have no photometric errors. And so in this case, you're able to really clearly see how the color magnitude diagram can allow you to dissect the ages of stars in order to, figure out the star formation rate of the population as a function of time. Each of the colors correspond to a different time bin, and these are in gigayears. And so by measuring high precision CMDs like this with Hubble Space Telescope and also James Webb, you're able to have very small photometric errors on the data, which allow you to measure these star formation rates precisely. However, because we're trying to actually measure the star formation rate over the entire cosmic time, we have to factor in the fact that these are galaxies and that their ISM metallicities change over time. And so not only do we have to measure star formation rate as a function of time, but historically we've also had to approximate or measure in some way the metallicity as a function of time. And so historically the way that this was done was that the metallicity as a function of time was fit at the same time, but the star formation rates did not factor directly into the chemical enrichment. So if you think back to the physical processes I talked about earlier, you would expect you form some amount of stellar mass, some amount of that is converted into metals, And so therefore, when you form a little bit of stellar mass, your metallicity that you're forming new stars at should go up by some commensurate amount. So these older models don't do this. And so what I wanted to do was to try and better connect the star formation history, so the star formation rates, to the actual chemical enrichment process. And so what I'm showing here are results, by the way, for the WLM galaxy. This is at a distance of 1 megaparsec, so it's local universe, and the stellar mass is roughly 4 times 10 to the 7. These are based on James Webb NIRCam data that were obtained with the Stellar Populations ERS program. And so for WLM, what we see is that the blue line now is this altered model where the chemical enrichment is linked directly to the star formation rates. And what you see is that, yeah, when you form a little bit of stars, you form a little bit of metals, and that tracks all the way through to, WLM shows this slight curtailing in the star formation rates for very recent times, and that's reflected also in the chemical evolution model. So we have this observational result, and so coming back to the theory, I'm working with a really great set of collaborators on TNG 50, so that's the 50 megaparsec box for illustrious TNG. Firebox, which uses the same Fire 2 model that Sarah and Megan talked about, but that's run in a cosmological volume, so that's actually comparable resolution to TNG 50. And also the Galacticus semi-analytic model, which is an entirely different type of theoretical model, and therefore it has certain advantages and disadvantages compared to hydrodynamic simulations. But with just one galaxy, I hesitate to conclude too much. But what's interesting to me is that these theoretical models generally agree at higher stellar masses, which is what you would expect if they're all able to reproduce the high mass present day MZR, right? But they diverge pretty significantly when you come down here into the dwarf range. And so as we add more galaxies to this, which we have data lined up to do, we should then be able to more consequently differentiate between these feedback models. Now we're going to need some different simulations to compare to in this regime because of how low stellar mass it is. But I've seen quite a few interesting talks this week on potentials for new collaborations here. And so with that, I'll wrap up, and I'll be happy to take your questions.
Great. Questions for Chris? Yes, Adam?
This is a fantastic talk, Chris. I can't state how much progress this is over what we have done in for many years, right? So I guess one very technical question is, you're aware that in Match, right, in Dolphin's Match software, we often assume a monotonic age metallicity relation, right, over the star formation history, which is what you showed, I think. With your self-consistent chemical evolution through the star formation history, do you think that we should think about a systematically lower metallicities that we've been recovering with that kind of assumption? Kind of seems like, at least at the younger ages, that might be a reasonable assumption.
I think that's possible. One reason I will say, I started out with a very simple MZR model. This is just a power law which matches the same extrapolation that's typically done. So it's literally a 2-parameter model. Ideally, when you start adding more data to this, you'll be able to constrain slightly higher parameter models, which can, I think, give you a little bit more information, because for WLM specifically, what sort of happens is, it hasn't had exactly constant star formation rate, but it's pretty constant. And so what happens is that the mass averaged metallicity is kind of the same, but when you track this through time, you can get, for example, different shapes in the distribution function that you predict for the metallicity, right? And so I don't know if it'll come out lower on average, but there are other benefits other than just, trying to get the mean metallicities better or something like that.
Mordecai?
So tracking metallicity from star formation history seems to gloss over the effects of the metal-rich winds. So how do you include that loss of metals in your final MPR?
So it's not explicitly parameterized. So one thing that I've been talking with people about are actually kind of related to the galactic chemical evolution. There are more complicated models for that include, inflow and outflow parameters and so forth. And so what I'm really fitting here is, there's a slope, and this is in terms of mass. And so you can convert this from, a logarithmic mass into a metal mass fraction into your Z, right? And then this slope tells you something about what the form of that Z as a function of T is. And the problem becomes that you don't have a historical constraint on the gas inflow, right? And so because the metallicities are always, metal content relative to hydrogen, if you don't have a historical constraint on what the hydrogen is, then the best you're ever kind of able to do is the relative abundance, right? And so ideally, when you add more galaxies to this, you would hopefully average out over individual galaxy variations in the H1 accretion. Does that make sense?
It still doesn't address the metal-rich outflow.
Maybe I didn't understand the question. Maybe we should talk after.
And I think we have time for one more question. Ben?
I think I can guess, but why are the models differing for their predictions for evolution at lower masses?
Well, so there are other known differences. For example, we haven't heard a lot about mass loading factors, but fire is kind of known for, you set off one or a couple supernova, and in fire they can entrain a lot of gas on the way out, and therefore they can push a lot of gas out of the ISM, whereas in other models that's not the case. And so if you're able to entrain a lot of metals on the way out, then you end up with lower metal abundances. It also has to do with what the metal loading factor of that outflow is, which is typically not, I don't remember quite as well what those numbers are.
Presumably the feedback prescription
Determines those two things, yeah.
Okay, great. Let's thank Chris again. Now we are going to set up for our poster session. So Steve, my poster guy, take it away.
Yeah, so I think what we're gonna so what we're gonna do is
All right, we're going to start off with Callum.
All right, hi everyone. I'm Callum. I'm a postdoc here, and I'm giving you a little poster presentation on recent work we've been doing on the Starburst 99 code. So if people are familiar, this is kind of used as population synthesis for starburst galaxies, anything that's star forming, making predictions of unresolved populations. So mostly focusing on young populations as well. So these are all massive stars, essentially. And I'm showing you that we've been updating the code, firstly, to move it from native Fortran to Python. Also, we've extended the metallicity range that the code covers. So before, you only had a couple of, well, basically it all depends on the input models. There's the stellar evolution and the stellar libraries have also been updated to get all these metallicities for these regions that you might be interested in. We've also extended the mass range, so you're including up to essentially stars of 300 solar masses as opposed to like 100 before. And I'm showing you some updates of predictions, for example, for ionizing flux, wind momentum, whatever parameter you're interested in. The side-by-side panels are showing you the effect of including rotation as well. And we're also making new predictions of actual stellar continuum spectra as well. So you can kind of see the new features, for example, carbon and helium, etc., that are popping up in the UV when you're adding in very massive stars. So So I think that's kind of all I wanted to say. If you're interested in the code at all, let me know. I'm happy to share it. Hopefully the paper will be coming out this month. And then, yeah, if you're also interested in chatting about anything massive stars, I worked a lot on O stars, fitting spectra, UV optical, infrared, mass loss rates, all that kind of stuff. If you want to know, your favorite O star spectral template to go for, that's also happy to chat. That's all. Thanks.
Next, we'll have Ilse Clark.
All right. Hello, everybody. My name is Ilse Clark. I'm a third-year graduate student at the University of California, San Diego, working with Karen Sandstrom. And today I'll be telling you about my work, the resolved structure of a low metallicity photodissociation region. So this PDR is the N13 PDR. It sits within the SMC at around 0.2 solar metallicity. We target this object with ALMA and near-spec, so we reach sub-parsec scales in this region for the first time in an extragalactic region. And so actually, this work offers the first resolved maps of a low metallicity photodissociation region for the first time that we can do it now with JWST. And so you can see that we target a couple different tracers. We target H0S1 line. We target the 3.3 PAW feature. We have some ALMA data as well. So we have CO J2 to 1, 12 CO J3 to 2, C1 1 to 0. We also have some H2 row vibrational lines. And you can see here that I've made a 3-color image, and I really want to point out the fact that the H2 1 to 0 line and the PAW 3.3 micron feature actually lay exactly on top of each other, unlike in Orion, actually. So we have basically resolved the ionization front, the dissociation front, and the C to CO transition with and made radio profiles trying to get the CO dark gas content in this region. And we actually find that for the SMC at this low metallicity, we have 5 times more CO dark gas than with a galactic PDR of the same parameters. So if you're interested in this work or YSOs, we have a YSO in this region as well, or just you want to look at some nice resolved maps of PDRs, please come see me in the cafeteria. So, thank you.
All right, now we have Dries.
Hi everyone, today I am presenting a paper that is in a series of the PDRs for All collaboration. So some of this work started when I was still here at Space Telescope. I have been away for a year now at Western University. So this PDRs for All collaboration has produced very high signal-to-noise spectra of the Orion bar PDR. And you can see a plethora of aromatic infrared bands there, or PAW bands, or whatever you want to call them. So in that collaboration, I've also been working on a tool called PAWFit. It is conceptually relatively simple. So it decomposes a spectrum into a continuum and then all the infrared bands. So using those Orion bar spectra, I have set up some settings for PAWFit, which I call the PDR pack. And I've applied, and I've also found that those settings work very well for some extragalactic star forming regions. So I show a spectrum of NGC 7469 as an example there. And then what I do, I apply my fit results of the Orion bar to try to quantify some of the profile variations of the 6.2 and 7.7 micron features that Charlotte already showed yesterday. And then, based on those fit results, you get some numbers that you can put into a diagram. And then I find that 5 regions in the Orion bar PDR, they have the same sequence for both of those quantities. So you can find kind of a gradual evolution in those profiles. And then I calculate the same quantities for the NGC 7469. And you can find that way, I show that those spectra resemble specific regions in the Orion bar PDR. There's also a small preview of the next application of this in NGC 7023. So if you want to talk about PDRs, or if you want to try to use this PDR pack and PAWFit, you can come see me at my e-poster.
All right, that's it for our flash talks. Do we have any announcements?
Yeah, this is fun. So we are now entering our morning break and poster session. So everyone be back by 11. And this is your last chance to vote on discussion ideas for this afternoon. So we've repopulated the board with all the ideas that we had yesterday we didn't talk about, and their votes, so you can add more, add votes on things, so we can have an awesome discussion again today, this afternoon. All right, great. Thank you all. See you in a half an hour.